Okay, let's dive right into this. Have you ever wondered what actually happens underground when we try to build a massive 13-story building on incredibly unpredictable soil right on the side of a steep slope? I mean, it's a giant engineering puzzle, and it's one that challenges structural professionals every single day. So in this explainer, we're going to break down a really fascinating investigation that transforms this huge structural dilemma into an elegant, heavily data-driven solution.
We're looking at a very real, very complex case study from the engineering firm Diatica. It's a 13-story building located in the Valle de Abu Ra in Colombia. And what makes this project so captivating is how we move from a terrifying macro challenge, the kind that literally keeps real estate developers up at night, to incredibly precise structural modeling. It's not just about, hey, will the building stand up? It's about mathematically understanding exactly how every single column behaves against the sheer brute forces of nature. Let's move to the agenda and see how this all builds together. First, we'll look at complex hillside construction, then the soil challenge. After that, we'll dig deep into the methodology, specifically open SysPy and random fields. Then we cover LRB isolation, seismic analysis results, and finally, life cycle cost. And trust me, the deep physics we're about to cover directly connects to some very real financial outcomes.
Right, so Part 1, Complex Hillside Construction.
Picture this scenario. We've got a 13-story reinforced concrete frame wall building. But because of the steep terrain, it obviously doesn't sit on a nice, flat, easy surface. It uses what engineers call a stepped foundation. Basically, the base physically steps down the hillside. Now, to the naked eye, that looks like a totally logical way to adapt to the land, right? But in high seismic zones, this geometry introduces massive, hidden risks from day one. So, the crucial point is this: the short column effect. A stepped foundation inevitably creates basement columns that are vastly different in length. In our Valle de Abu Ra case study, this creates a staggering 27-to-1 stiffness ratio between those columns. 27-to-1! During an earthquake, the force doesn't just spread out evenly. Those shorter, hyper-rigid columns end up absorbing a wildly disproportionate amount of shear force. For traditional fixed-base designs, this is essentially a fatal flaw. It leads straight to brittle and catastrophic failure.
Which brings us to Part 2, the soil challenge.
Forget textbook models with perfectly uniform layers of earth. That's not reality here. We are dealing with colluvial soil. It's a highly heterogeneous, totally chaotic mix of mud, clay, and giant boulders. This extreme variability generates random torsional eccentricities. Think about it. When the earth shakes, one side of the building might be sitting on solid rock while the other is basically on soft mud. That causes the entire structure to twist violently. Traditional, uniform soil models simply fail to predict this kind of subterranean chaos.
So, how do we solve this? Let's get into Part 3, methodology using open SysPy and random fields.
To accurately model this reality, we need cutting-edge precision. The step-by-step methodology here is absolutely brilliant. Step 1 is building a rigorous, nonlinear 3D model using open SysPy. This software simulates exactly how the concrete and steel deform, crack, and yield under extreme tension in a fully 3D space. But Step 2? Well, that's where the real magic happens. It's the implementation of the random field for the soil. Instead of just assuming the ground is static, the engineers used an exponential covariance with a correlation length of about 8 meters to map out the soil stiffness. And to make sure they captured all the crazy unpredictability of that colluvial soil, they ran 1,000 Monte Carlo simulations. That's 1,000 completely different scenarios, iterating through the math to find the true statistical response of how that soil variability would twist the structure. It's a level of computational detail that literally separates hoping for the best from absolute engineering certainty.
Okay, Part 4, LRB isolation.
So, the solution they implemented is base isolation using lead rubber bearings, or LRB. But there's a really critical detail here. Relying on simplistic or isothermal isolator models is frankly dangerous. Instead, the Diatica engineers utilized the lead rubber X thermomechanical model. Why does heat matter so much? Well, during long-duration subduction quakes, think of the devastating 2010 Maule earthquake. That constant back-and-forth motion severely heats up the lead core of the isolators. And as it heats up, its strength degrades. This advanced model captures that specific heat-induced strength loss, ensuring the resilience data is rock solid even in the absolute worst, longest seismic events imaginable.
Now, Part 5, Seismic Analysis Results.
Now, what's really interesting about this contrast is how stark it is. With a traditional fixed-base design, under the design seismic load, that 27-to-1 stiffness ratio we talked about proves completely fatal. The building suffers a brittle shear failure in just 5.84 seconds. Basically, total collapse before the earthquake is even fully underway. But with the LRB isolated structure, not only does it survive, but the system actively recenters itself. That massive, destructive twisting caused by the colluvial soil is drastically reduced from an alarming 18.4% down to a highly manageable 3.2%. The isolation essentially uncouples the building from the unpredictable whims of the ground beneath it.
If you want to take away one single number that summarizes this engineering triumph, it's 96%. That is the massive reduction in basal shear. The raw, brute force hitting the bottom of the building drops from a staggering 4,230 kilonewtons to just 158 kilonewtons. That is a monumental victory. It completely changes the game.
Because we're reducing that force by 96%, we see dramatic structural improvements across the board. The fundamental period of the building shifts from 1.48 seconds up to 2.82 seconds, effectively moving it safely away from the earthquake's most destructive resonant frequencies. And the maximum drift, meaning how much the building actually leans from floor to floor, plummets from 2.1% to barely 0.45%. And that number is absolutely vital because it means the building hits immediate occupancy status. After a massive earthquake, the structure isn't just barely standing, it is completely functional. People can safely stay inside or re-enter without needing any major structural repairs.
Which brings us to our final section, life cycle cost. And this brilliantly illustrates the conversation every structural engineer really needs to have with real estate developers. Yes, implementing base isolation and this top-tier level of computational engineering increases the upfront capital expenditure, the CapEx, by about 11%. But look at the return on that. That 11% upfront bump yields a staggering 92% reduction in expected annual loss, or EAL. We are talking about gigantic financial savings in repairs, operational downtime, and insurance over the life of the building.
To put that into a long-term perspective, taking this analytical, preventative approach prevents asset value losses of over 45% across a 50-year lifespan. It really is the ultimate protection. It's not just about protecting human life by preventing a structural collapse, which is of course paramount, but it's also the absolute protection of a multi-million-dollar financial investment over decades.
All of this leaves us with a pretty crucial reflection. Seeing how a stepped topography and heterogeneous soil can completely destroy a fixed-base design in under 6 seconds, we have to ask, are traditional prescriptive design codes currently failing your hillside projects? Perhaps it's time we stop guessing about complex soil behavior and start modeling reality with the advanced analytical tools we now have right at our disposal. Thanks so much for joining me on this visual explainer. I really hope it gave you a completely new perspective on what it truly means to build with resilience.